Good afternoon. I'm Roger Kuhns, economic geologist with Maston Aerospace Systems in Mojave, California. This presentation is our work on practical and economic rocket mining of lunar ice. Maston is in collaboration with Philip Metzger with the University of Central Florida, Kris Zacny with Honeybee Robotics, and Noah Rhys with Yeti Space. Maston is the lead on this project. In this presentation, I will outline the team's goals of targeting and testing lunar ice resources, examining regolith and resource heterogeneity, defining ore challenges, describing Maston's rocket mining system, look at why it is better than mechanical excavation methods, review our preliminary mining and economic models, and of course, present our conclusions. Let's start with targeting and testing. We know from NASA's Lunar Reconnaissance Orbiter remote sensing data and that of other programs that water ice exists on and in the regolith. We know that it collects in permanently shadowed regions, shown here in blue within craters at the lunar South Pole. We also have an early understanding that this type of target presents significant technical and economic challenges if we are to recover water ice from the PSRs and zones within the lunar soil and regolith. This is why our team anticipates a robotic mission to the lunar South Pole that builds upon the remote sensing and very limited sampling data to date. The mission has a preliminary target landing site in the area of Shackleton and de Gerlache craters. The mission would refine remote sensing data and continuously assess water ice traps as we improve our understanding of the resource. Once the mining rover is on site, it would conduct a daily routine as follows. Overburden removal and recovery utilizing short rocket pulse brushing, rocket mining into the regolith via pulsed excavation under a containment dome, collection of regolith geotechnical data, sample collection of frozen volatiles on a cold plate unit, and chemical analyses of the collected volatiles, and transmission of the data back to Earth. Regolith and resource heterogeneity. Let's examine that briefly now. Data, mostly from Apollo missions and more recent NASA and other missions, show us that the water ice is and can be trapped in a number of surface and subsurface situations. The best known are the superficial ice crusts in the permanently shadowed regions, natural cold traps, within craters and behind other topographic features, as shown in this schematic and in Set A. But perhaps the most significant water ice resources occur below in the regolith. Water ice can occur interstitially between regolith grains as shown in B from Colapret et al. 2010. There are innumerable porosity traps in the regolith, including vesiculated basalts, shown in C, and heterogeneous breccias, shown in D, both samples from Apollo 15. Potentially open or receptive fractures, shown in yellow around the crater, and in E, are also present in the regolith. These features and others create a complexity of water ice traps that must be considered in any mining venture. Now, another feature of superficial frozen volatile crusts. They are not stable. They move. Look at this annular variation, run on a repeating cycle to show the changes, in water ice crusts from the LRO LEND neutron detector data between 2009 and 2012. Note how the crusts vaporize and reform, creating a moving target for any recovery operation. This requires any mining platform to be mobile and versatile. Defining ore challenges. Not only do the locations of frozen volatile crusts shift over time, but they are variable in thickness, variable in component concentrations, such as water and other components, as shown here in the Moon Mineralogy Mapper. Here you see a relatively concentrated and relatively dispersed abundance or non-abundance of frozen water. And there is the probability of recovery. Permeability, porosity, and accessibility offer a big challenge here. In this block diagram example, let's utilize the infrared reflectance data and consider the indicated presence of water ice as a resource we'll investigate. The data tells us nothing about the subsurface resource, but let's assume surface and subsurface resources are connected to some degree for this example. And in this example, we'll define a mining block based on our preliminary robotic mining rover testing, that which I showed you earlier. And in these tests, we can define various levels of confidence of water-ice resources. They range from inferred, where we are today, to indicated and probable and measured and eventually proved, depending on the level of sampling and analytical data that defines whether or not the resource is just a resource, not economic, or an ore body, able to be economically mined for a profit. Now, with this backdrop of challenges, let's look at Maston's rocket mining system. The system architecture for excavation and capture of the water involves the novel use of rocket engines. Precision firing of a short burst rocket creates deep cratering, disaggregation of regolith, sublimation of frozen volatiles, and capture via condensation in the collection vessel. Maston's approach utilizes this deep cratering phenomenon. Deep cratering creates the shock diamond effect observed here on Earth and results in rapid and vigorous excavation of regolith down to the length of the plume in as little as 0.3 seconds. For a 100-pound-foot rocket engine, this can be up to 3 feet deep in less than a second and will be able to excavate many types of regolith. This method allows fluidization of regolith around larger particles and boulders, freeing up a larger percentage of volatiles from pore spaces, crusts, and breccias without having to excavate all of the components of the regolith. This can be seen in tests with Maston's Zodiac rocket engine. Maston has demonstrated removal rates of 30 kilograms per second for a small rocket thruster with gaseous propellants during tests of lunar regolith simulant. Again, shown here in the firing tests, craters were excavated rapidly, creating conical to steep-sided excavations, like cylinders, as a highly efficient regolith fluidization mechanism. This will disrupt surface ice and soil, exposing frozen layers or pockets and areas of heterogeneous porosity to direct convective heating as shown in these Maston firing tests and diagrams. This will enable heating of 2,000 kilograms of regolith and vaporization of 20 kilograms of water at 1% grade and yield in 116 seconds of engine fire time. That's 100 megajoules of chemical energy input. This is enough hot fire time to churn the soil, followed by other heating methods to augment the process and raise the regolith from ambient to 200 degrees Kelvin. The overall rocket mining array with mobile processor facilities, product storage, and space tugs are shown here. With this knowledge of the innovative utilization of rockets in mining, let's touch base on how this is more practical in many ways than mechanical excavation methods. This short video is one of my deep-sea mining projects. That's me by the large excavator. Shown here is the power and sheer massive engineering design needed to crush sediment containing particle sizes from sand to boulders, much like regolith. This excavator is heavy, requires significant maintenance, and is expensive. This, or even smaller versions, would be difficult to pull off economically on the moon. Maston has built a preliminary mining and economic model that considers all of the challenges I've shown you in this talk. Key to profitable mining is a focus on low-risk areas, low-relief areas, consistent subsurface resources, that's grade and tonnage, consistent geology for consistent mining, access to sunlight for energy, and few communication barriers. These guide us towards a comparatively low-cost, low-maintenance, and versatile mining system. Rocket mining offers this. In our model, we designate mining blocks designed around the rocket mining cratering array as the mobile rocket mining rover moves over the confirmed water, ice, or zone. In this example, we have a 100 meter by 10 meter block that contains 42 craters, or mined cones. The anticipated mining rate is 1 cone, or crater, per day. As you saw in the test firing videos and photographs, crater or cone excavation occurs rapidly. In this example, we have a cone, conservatively rather than a cylinder, as a mined portion of the regolith. The mining rate for this cone is just under 13 metric tons per hour and can be mined in one 20-hour day. The economics to rocket mining are shown here in this preliminary model. We've assumed water ice grades of 1%, 5%, and 10%. and product value at $10,000 per kilogram of water. This mining cycle would be 42 days and yield a gross income between $680 million and $6.8 billion, depending on the grade. Cash flow analysis suggests the potential for a reasonable profit, indicating rocket mining will be economically viable and provide a healthy return on investment. All of this, of course, is being refined as we develop the technology and learn more about the resource. In conclusion, rocket mining offers an elegant solution to mining in a challenging environment. It offers less infrastructure, lower maintenance, versatility, less energy demand, lower cost, and favorable economics, and we think could be a key component to starting a realistic lunar economy. Thank you very much, from me and the team.